Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. Imagine, if you will, the sun beating down upon the sands of Egypt. The year is 1798. A young Joseph Fourier, a scholar amidst a sprawling French expedition led by Napoleon Bonaparte, grapples with a problem far removed from the familiar confines of European academia. He is tasked with understanding, with quantifying, the very essence of heat transfer within this dramatically different environment. The intense solar radiation, the varying thermal properties of the desert landscape, the complex interactions of temperature across diverse materials, all presented a formidable challenge. This was not experimentation conducted within the controlled setting of a laboratory, but fieldwork in the most demanding sense, where the vagaries of nature constantly threatened the integrity of any observation. Prior to this pivotal journey, Fourier's intellectual energies were primarily directed toward pure mathematics, specifically toward the solving of equations. In truth, these early investigations appeared to have little immediate connection to the physical world. He explored abstract relationships, developed innovative techniques for manipulating algebraic expressions, and sought elegant solutions to problems seemingly detached from practical application. These were the pursuits of a mind deeply engaged with the internal logic and beauty of mathematics itself. Yet, these formative experiences provided the essential toolkit for his later groundbreaking work. The central problem of heat conduction emerged as a scientific enigma during this period. How does heat propagate through a solid object? How can one predict the temperature distribution within a body subjected to various thermal influences? The prevailing scientific understanding at the time was rudimentary, relying heavily on qualitative observations and lacking a comprehensive mathematical framework. Scientists possessed limited tools to accurately describe, let alone predict, the behavior of heat. This essay will explore the life and profoundly influential work of Joseph Fourier, tracing his intellectual journey from abstract mathematical explorations to his revolutionary theory of heat. We will examine the historical context in which his ideas arose, the specific challenges he confronted, and the ingenious solutions he devised. We will delve into the mathematical underpinnings of his theory, highlighting its enduring impact on modern science and engineering. The scope of this exploration encompasses Fourier's contributions to both mathematics and physics, with a primary emphasis on his theory of heat and its mathematical foundations. Fourier's work was transformative. His analytical approach provided the foundation for countless subsequent advances across diverse scientific and engineering disciplines. From understanding the Earth's climate to designing efficient engines, from medical imaging techniques to the development of modern communication systems, the echoes of Fourier's insights resonate throughout the modern world. The expedition to Egypt itself provided a unique crucible for Fourier's intellectual development. The practical challenges of understanding heat transfer in such a complex environment forced him to confront the limitations of existing scientific knowledge. He recognized the need for a more rigorous, mathematically grounded approach. He began to formulate his ideas, initially driven by the immediate demands of the expedition, but ultimately leading to a theory of far-reaching significance. Following his return from Egypt, Fourier dedicated himself to the rigorous mathematical formulation of heat transfer. He sought to create a comprehensive model capable of predicting the temperature distribution within a solid body under arbitrary conditions. This endeavor required him to develop entirely new mathematical techniques, to push the boundaries of existing knowledge, and to challenge long-held assumptions about the nature of mathematical solutions. Central to Fourier's approach was the idea of representing complex temperature distributions as sums of simpler, oscillating functions. This seemingly audacious proposition, now known as Fourier analysis, allowed him to transform the problem of heat conduction into a more tractable mathematical form. It enabled him to solve the equations governing heat flow and to predict the temperature at any point within a body at any given time. The impact of Fourier's work extended far beyond the immediate problem of heat conduction. His mathematical techniques found applications in a wide range of fields, including acoustics, optics, signal processing, and image analysis. Fourier analysis became an indispensable tool for scientists and engineers across diverse disciplines, enabling them to understand and manipulate complex phenomena. The structure of our exploration will proceed as follows. We will first examine the mathematical landscape prior to Fourier's contributions, highlighting the key concepts and challenges that shaped his work. We will then delve into the details of Fourier's theory of heat, exploring its mathematical foundations and its physical implications. Next, we will consider the initial reception of Fourier's ideas, examining the debates and controversies that surrounded his work. Finally, we will assess the enduring legacy of Fourier's contributions, tracing their impact on modern science and engineering. His theory provides a powerful framework for understanding a wide range of physical phenomena. It allows scientists to model the flow of heat in complex systems, to predict the behavior of materials under extreme conditions, and to design more efficient energy technologies. Engineers rely on Fourier's principles to optimize the performance of everything from microchips to skyscrapers. Furthermore, Fourier's work exemplifies the profound interplay between mathematics and physics. His insights demonstrate the power of mathematical abstraction to illuminate the workings of the physical world. He showed how seemingly abstract mathematical concepts can provide a deeper understanding of concrete phenomena. The tools he developed are used to analyze data, compress information, and extract meaningful insights from complex datasets. From medical imaging to financial modeling, Fourier's analysis plays a crucial role in shaping our understanding of the world. The journey to understanding heat, initiated on the sands of Egypt, ultimately transformed our understanding of the universe. Joseph Fourier's legacy endures, a testament to the power of human intellect to unlock the secrets of nature. His work continues to inspire scientists and engineers to push the boundaries of knowledge and to create a better future. He offered a new way to view the world, a way that continues to shape our understanding of science and technology. To fully appreciate the revolutionary character of Fourier's work, one must first inhabit the intellectual landscape he entered. The turn of the 19th century was a period of immense mathematical confidence, a world still basking in the brilliant afterglow of the Enlightenment. The titans of the preceding century, Newton, Leibniz, the Bernoulli family, and above all the colossus Leonhard Euler, had bequeathed a formidable inheritance: the calculus. This was the powerful engine of the new physics, a language seemingly capable of describing everything from the swing of a pendulum to the majestic orbits of the planets. It had transformed the study of motion from a descriptive art into a predictive science, built upon the rigorous foundation of differential equations. The primary triumphs of this era lay in the domain of what we now call ordinary differential equations. These are the equations that govern systems depending on a single variable, typically time. Euler, in his characteristically exhaustive fashion, had systematized their study, developing methods for solving vast classes of these equations. His work on linear equations with constant coefficients, and his elegant method of variation of parameters, provided a toolkit of extraordinary power. Mathematicians like Lagrange and Laplace extended this work, applying it with breathtaking success to celestial mechanics. Rousseau's ideas about popular sovereignty and the general will also influenced Muir's thinking. Rousseau argued that political authority should ultimately reside in the people as a whole, and that laws should reflect the general will of the community. Muir embraced this concept, believing that the Scottish people should have the right to determine their own political destiny. He saw parliamentary reform as a means of empowering the people and ensuring that their voices were heard in government. Montesquieu's theory of the separation of powers also played a role in shaping Muir's political philosophy. Montesquieu argued that government should be divided into three branches: the legislative, the executive, and the judicial, each with its own distinct powers and responsibilities. Muir believed that this separation of powers was essential for preventing tyranny and protecting individual liberty. He saw the existing political system in Scotland as lacking a proper separation of powers, with the executive branch wielding too much power and the legislative branch being too easily influenced by the aristocracy. Muir's legal background further informed his understanding of rights and justice. As a lawyer, he was intimately familiar with the laws of Scotland and the legal system. This knowledge allowed him to articulate his arguments for political reform with clarity, precision, and a deep understanding of the legal and constitutional framework. He was able to identify specific laws and practices that he believed were unjust or oppressive, and he could offer concrete proposals for reform. His legal training also gave him a keen appreciation for the importance of due process and the rule of law. He believed that all individuals, regardless of their social status or political beliefs, were entitled to fair treatment under the law. Muir's belief in the inherent rights of the people and the need for accountable government is evident in his writings and speeches. He consistently argued that government should be based on the consent of the governed and that citizens should have the right to participate in the political process. He also emphasized the importance of transparency and accountability in government, arguing that public officials should be held responsible for their actions. In one of his most famous speeches, Muir declared, "I have devoted myself to the cause of the people. It is a cause I am free to confess, which I have long regarded as the most sacred and important that can engage the attention of mankind." This statement encapsulates Muir's unwavering commitment to the principles of democracy and his belief that the people should be the ultimate source of political authority. Muir's writings also reveal his deep concern for the plight of the poor and the marginalized. When an object was heated, it expanded because caloric fluid, flowing into the pores of the material, pushed its constituent particles apart. Temperature was a measure of the concentration or density of this caloric. The mixing of hot and cold water was easily visualized as the caloric fluid redistributing itself until a uniform concentration, and thus a uniform temperature, was achieved. The caloric theory provided a tangible, mechanical, and intuitive picture of thermal processes. It was a masterpiece of 18th-century scientific reasoning, offering a unified framework for what would otherwise be a disconnected collection of observations. Its influence was so profound that heat capacity was conceived as the capacity of a substance to hold caloric fluid, and the concept of latent heat, the energy absorbed or released during a phase change, was explained as caloric becoming bound to the particles of the substance. Yet, for all its explanatory power, the theory carried the seeds of its own demise. Observations by figures like Benjamin Thompson, Count Rumford, at the end of the 18th century, presented a serious puzzle. While boring a cannon, Rumford observed that a seemingly limitless amount of heat could be generated by friction. If caloric were a conserved substance, where was all of this fluid coming from? The idea of heat as a form of motion was an old one, but the caloric theory held such sway that these contrary observations were, for a time, treated as anomalies awaiting a more sophisticated explanation within the caloric framework. Here, then, was the stage upon which Fourier would make his entrance. On one side, a mature and powerful calculus, masterful in its handling of time-dependent systems, but struggling at the frontier of spatio-temporal change. On the other, a compelling and widely accepted physical theory of heat as a conserved fluid, a theory that practically begged for a mathematical description of its flow. The central, unanswered question was how to unite these two domains. How could one model the propagation of caloric through a solid body? The temperature at any point inside a metal bar, for instance, would depend on its position along the bar and on the passage of time. This was unequivocally a problem for a partial differential equation. Yet the specific form of this equation was unknown, and even if it could be formulated, the methods for solving it for a general case, with arbitrary initial temperature distributions, were entirely lacking. The intellectual challenge was twofold. First, to translate the physical principles of heat flow as understood through the lens of caloric theory into a precise mathematical statement. They could model the solar system as a collection of point masses, their positions evolving in time according to Newton's law of gravitation, expressed as a system of ordinary differential equations. The universe, it seemed, was a grand and intricate clockwork, and its workings could be deciphered by solving for functions of time. This very success, however, circumscribed the types of problems that received the most attention. The focus remained on phenomena that could be idealized as evolving in time alone. The challenge of describing phenomena that varied continuously in both space and time represented a frontier of profound difficulty. These are the realms of partial differential equations, where the unknown quantity is a function of multiple independent variables. The conceptual leap is immense. The solution to an ordinary differential equation is a curve, a path traced through time. The solution to a partial differential equation is a surface or a field, an entire landscape of values evolving and undulating. The mathematical arsenal for taming such beasts was, at the time, sparse and specialized. Pioneering forays had been made, of course. John Le Bon d'Alembert, in the 1740s, had derived the one-dimensional wave equation to describe the vibrations of a string. This was a seminal moment, the birth of mathematical physics as we know it. The equation itself, stating that the second partial derivative of the displacement with respect to time is proportional to its second partial derivative with respect to position, was a thing of beauty. Yet its appearance immediately ignited a fierce debate, drawing in Euler and Daniel Bernoulli, concerning the very nature of a function. What kinds of solutions were permissible? Could a function be pieced together from different algebraic expressions and still be a valid solution? The controversy over the vibrating string revealed that partial differential equations raised deep and unsettling questions about the foundations of analysis itself. The tools for a general theory were absent. Each new partial differential equation that arose from a physical problem appeared as a unique monster, requiring its own bespoke, ad hoc methods of attack, if any could be found at all. This mathematical context was paralleled by a specific and pervasive physical theory concerning the nature of heat. The dominant model of the day was the caloric theory, championed by the great chemist Antoine Lavoisier. This theory posited that heat was a substance, an imponderable self-repelling fluid called caloric. This ethereal substance was thought to be conserved, flowing from hotter bodies to colder bodies, much like water flowing downhill to find its level. The theory was remarkably effective at explaining a wide range of thermal phenomena. Second, and far more daunting, was the task of inventing the mathematical machinery required to solve that statement, a task that would force a complete re-evaluation of the meaning of a function and the representation of physical reality. This was the chasm Fourier confronted, a gap between the physical intuition of his time and the existing capabilities of its mathematics. His life's work would become the construction of a bridge across it, Fourier's first monumental step was to crystallize the vague physical intuitions about heat into the hard, unforgiving language of mathematics. He began with a set of carefully articulated physical principles, axioms derived from observation and the prevailing caloric theory of his day. This theory, though later superseded, imagined heat as a weightless conserved fluid that flowed from regions of higher density to regions of lower density. The genius of Fourier's approach lay in his ability to see past the specific physical model and abstract the underlying mathematical relationships that would endure even after the theory of caloric fell away. His reasoning proceeded with a beautiful reductionist logic. He considered the flow of heat between infinitesimally close points within a solid body. The fundamental principle was that the rate of heat flow between two adjacent molecules is proportional to the difference in their temperatures. This is a local rule. To scale this up to a macroscopic object, Fourier had to consider the net effect of this flow on a tiny volume element within the material. The temperature of this small cube of matter could only change if the amount of heat flowing into it was different from the amount flowing out. An equilibrium of flow would mean a stable temperature. A change in temperature, therefore, must be caused by an imbalance, a net influx or efflux of caloric. This physical reasoning led him directly to the calculus of partial derivatives. Let us denote the temperature at any point within the object by the function v, which depends on the spatial coordinates x, y, and z, and also on the time t. The rate at which the temperature changes at a specific point is captured by the partial derivative of v with respect to time, a term spoken as the partial derivative of v with respect to t. This term represents the temporal evolution of the system. The spatial variation of temperature is what drives the flow. A uniform temperature throughout the object would result in zero flow. The flow is driven by a temperature gradient in one dimension, say along a thin metal bar. This is simply the derivative of temperature with respect to position. In 3 dimensions, this becomes the gradient vector, whose components are the partial derivatives of v with respect to x, y, and z. Fourier postulated that the flux of heat, the amount of heat energy crossing a unit area per unit time, is directly proportional to this gradient. Heat flows downhill, from hotter to colder, in the direction opposite the gradient. The final crucial step was to connect these two ideas using the principle of conservation of energy, or in his terms, the conservation of caloric. The rate of temperature increase within an infinitesimal volume, our partial derivative with respect to time, must be equal to the net rate at which heat flows into that volume. This net flow is determined by how the heat flux itself changes from point to point. A uniform flux would mean as much heat enters one side of our tiny cube as leaves the other. A change in temperature requires a change in the flux. In the language of vector calculus, this net influx is described by the divergence of the heat flux vector. Since the flux is proportional to the gradient of the temperature, the net influx is proportional to the divergence of the gradient. This chain of physical reasoning, translated into mathematics, culminates in one of the most elegant and powerful equations in all of physics. The divergence of the gradient is an operation known as the Laplacian, represented by the symbol nabla squared. So the complete statement becomes the partial derivative of temperature with respect to time is proportional to the Laplacian of the temperature. Spoken fully, for a temperature v as a function of x, y, z, and t, the equation reads, the partial derivative of v with respect to t equals a constant, k, multiplied by the sum of the second partial derivatives of v with respect to x, y, and z. The constant k, which Fourier introduced, is the thermal diffusivity, a parameter that encapsulates the material properties of the object, how readily it conducts heat relative to its capacity to store it. This is Fourier's heat equation. It is a linear parabolic partial differential equation. Its linearity means that if one has two separate solutions, their sum is also a solution, a property of immense consequence for the method he would later develop. Its parabolic nature implies that disturbances, changes in temperature, propagate at an infinite speed. A change in temperature at one point in the body is felt, however minutely, at every other point in the body instantaneously. This is, of course, a mathematical idealization, a consequence of the model's assumptions, yet it provides an astonishingly accurate description for a vast range of physical phenomena. With this equation, Fourier had captured the essence of thermal diffusion in a single deterministic statement. He had created a universal law for the propagation of heat within solids. However, an equation of this type is a mere skeleton. It describes a family of possible behaviors. The classical methods of solving differential equations, which often yielded a single neat analytical formula, seemed insufficient for a problem where the starting condition could be as complex as a sudden pulse of heat applied to one section of a rod, or a jagged, uneven temperature profile across a metal plate. The solution required a tool of unprecedented flexibility, a mathematical key capable of unlocking an infinite variety of initial states. Fourier's approach was one of profound, almost audacious, conceptual simplicity. He began with the linearity of his own equation. The principle of superposition, a direct consequence of this linearity, dictates that if one has several valid solutions to the heat equation, their sum is also a valid solution. This property was well understood. Fourier's genius lay in his extension of this principle to its ultimate conclusion. He sought to construct his general solution from an infinite sum of elementary or fundamental solutions. He observed that functions of the form, the sine of n times pi times x divided by L, or the cosine of n times pi times x divided by L, where L is the length of the rod and n is an integer, behaved very gracefully when subjected to the heat equation. When paired with an appropriate time-dependent term, specifically the exponential e to the power of negative k times n squared times pi squared times t divided by L squared, they formed a family of solutions that satisfied both the differential equation and the boundary conditions of zero temperature at the ends. Each of these elementary solutions represents a simple standing wave of heat, a smooth periodic temperature profile that decays over time. The revolutionary leap was this: Fourier proposed that any arbitrary function representing any conceivable initial temperature distribution could be decomposed into and represented by an infinite sum of these simple sine and cosine waves. This proposition, which would become the cornerstone of Fourier analysis, was a radical departure from the mathematical orthodoxy of the early 19th century. He asserted that a function f of x describing the temperature at position x at time 0 could be written as an infinite series. This series takes the form of a constant term, a sub-zero divided by 2, plus the summation from n equals 1 to infinity of the quantity a sub n times the cosine of n pi sev over L, plus b sub n times the sine of n pi sev over L. This was more than a mathematical technique, it was a new way of seeing. It suggested that even the most complex and irregular shapes could be viewed as a superposition of pure, simple harmonies. The coefficients of this series, the a sub n and b sub n terms, act as the weights or amplitudes for each harmonic component. They determine how much of each specific sine or cosine wave is needed in the grand synthesis to reconstruct the original function, and Fourier provided the explicit recipe for calculating these coefficients. He showed that each coefficient could be extracted from the original function f of x through integration. For example, the coefficient sub n is proportional to the integral from negative L to L of the function f of x multiplied by the cosine of n pi x over L. This integral acts as a mathematical filter, isolating the strength of one specific frequency component from the chaotic whole. When Fourier presented his initial findings to the prestigious French Academy of Sciences in 1807, the reception was one of deep skepticism, bordering on dismissal. The judging committee, which included luminaries like Lagrange, Laplace, and Legendre, was steeped in a tradition that viewed functions as single, continuous, and infinitely differentiable analytical expressions. The idea that a series of smooth, well-behaved sine and cosine functions could converge to a function with sharp corners or even outright discontinuities. For example, a function representing a rod heated in one section and cold in another seemed absurd. Lagrange, in particular, was a staunch opponent. He had worked with trigonometric series himself and had concluded that such a representation was possible only for a very limited class of functions. Fourier's universal claim struck him as mathematically unsound, a piece of physical intuition that lacked the necessary analytical rigor. The Academy acknowledged the importance of his work on heat diffusion, but withheld its full endorsement of the mathematical methods, citing a lack of generality and rigor. Undeterred, Fourier continued to refine and expand his theory. The power of his method was undeniable. Once the initial temperature distribution f of x was decomposed into its Fourier series, the solution to the heat equation for all subsequent times unfolded with beautiful clarity. Each sine and cosine term in the initial series was simply multiplied by its corresponding exponential decay factor. The terms with high ns representing high-frequency spatial variations, sharp corners and rapid wiggles in the temperature profile were multiplied by decay factors that diminished very rapidly with time. The terms with low ns representing the broad, smooth features of the temperature distribution decayed much more slowly. The mathematics thus provided a stunningly accurate picture of the physical process. It showed precisely how sharp temperature gradients smooth out almost instantly, while the overall heat energy dissipates gradually throughout the object. A jagged initial profile would within moments become smooth and rounded, eventually settling into a simple, gentle curve as it cooled. Fourier's series provided a quantitative, predictive account of this evolution, something no previous theory could accomplish. The central question of convergence, however, lingered for decades. Fourier himself, operating with the powerful intuition of a physicist, was convinced of the general validity of his series, but a formal proof remained elusive. The mathematical community required a precise statement of the conditions under which an arbitrary function's Fourier series would indeed converge back to the function itself. This crucial piece of the puzzle was eventually supplied by the German mathematician Peter Gustav Lejeune Dirichlet in 1829. Dirichlet, with a new level of analytical precision, established a set of sufficient conditions for convergence. He proved that for any function that is piecewise continuous and has a finite number of maxima and minima within a given interval, a set of conditions that covers virtually every physically realistic scenario, its Fourier series converges. It converges to the value of the function at points of continuity and to the average of the limits from the left and right at points of discontinuity. Dirichlet's work placed Fourier's revolutionary ideas on an unshakable logical foundation. It legitimized the method in the eyes of pure mathematicians and transformed the Fourier series from a controversial tool of physics into a central pillar of mathematical analysis, opening a new epoch in the study of functions and infinite series. With Dirichlets' proof providing a rigorous charter, the Fourier series was fully emancipated from the specific physical circumstances of its birth. The central, electrifying idea that a complex function could be resolved into a sum of simple, pure sinusoids was now a certified principle of mathematical analysis. This intellectual liberation invited a monumental question: if this decomposition was possible for functions confined to a finite interval, for phenomena that repeat themselves in a periodic cycle, what of functions that stretch across all of space or time? What of the singular, a periodic event, the clap of thunder, the flash of a camera, the decay of a radioactive particle? The very structure of the Fourier series, with its discrete harmonics built upon a fundamental frequency tied to the length of an interval, seemed ill-suited for such boundless non-repeating forms. The path forward required a conceptual leap of profound elegance. One can imagine the finite, insulated rod from Fourier's original problem being stretched, its length L approaching infinity. As the interval expands, the fundamental frequency, which is inversely proportional to L, becomes vanishingly small. The discrete harmonics, once spaced apart like integers on a number line, grow ever closer together. In the limit, as the interval becomes infinite, the separation between successive frequencies becomes infinitesimal. The sum over discrete frequencies, the very essence of the Fourier series, metamorphoses into an integral over a continuous spectrum of frequencies. This is the genesis of the Fourier transform. The Fourier transform is the grand generalization of the Fourier series. It takes a function, typically a function of time, let us call it phi of t, and produces a new function, f of omega, which describes the amplitude and phase of each frequency component, omega, present in the original signal. The transform is expressed as an integral from negative infinity to positive infinity of the original function, f of t multiplied by a complex exponential, e to the power of negative I omega t, integrated with respect to time. The result is a mapping from the familiar time domain into the frequency domain. This new domain offers a completely different and profoundly insightful perspective on the nature of the function. It is akin to a mathematical prism, where a glass prism takes a beam of white light and refracts it into its constituent spectrum of colors. The Fourier transform takes a complex signal, a sound wave, an electrical current, a stock market fluctuation, and decomposes it into its fundamental sinusoidal frequencies. The implications of this were, and remain, staggering. The ability to view any signal through the lens of its frequency content revolutionized entire fields of science and engineering. In the world of signal processing, the Fourier transform became the bedrock analytical tool. It allows an engineer to analyze the waveform of a human voice, identify the dominant frequencies that form a particular vowel sound, and then design filters to remove unwanted background noise, which occupies a different part of the frequency spectrum. It is the principle that underpins radio communication, where information is encoded by modulating a high-frequency carrier wave, and then decoded at the receiver by analyzing the frequency content of the incoming signal. This power extends into the visual realm. A two-dimensional version of the Fourier transform can be applied to images, where it decomposes the image into its constituent spatial frequencies. High spatial frequencies correspond to sharp edges and fine details, while low frequencies represent smooth, gradual changes in color or brightness. This insight is the conceptual heart of image compression standards like JPEG. By performing a Fourier-like transform on small blocks of an image,
The algorithm can identify and discard the high-frequency information that the human eye is less sensitive to, thereby achieving remarkable compression with minimal perceptible loss of quality. The image we see is stored and transmitted as a recipe of spatial frequencies. The influence of Fourier's thinking permeated the foundations of modern physics. In the nascent world of quantum mechanics, Werner Heisenberg's uncertainty principle found a natural mathematical home in the language of Fourier analysis. The principle states that one can measure the position of a particle with high precision or its momentum with high precision, but one can never know both simultaneously with perfect accuracy. This physical limitation is a direct analogue of a fundamental property of the Fourier transform. A function cannot be arbitrarily concentrated in both the time domain and the frequency domain. A signal that is very short in duration, like a sharp pulse, must necessarily be composed of a very wide band of frequencies. Conversely, a signal with a very narrow frequency band, a pure tone, must extend over a long duration. Position and momentum, in the quantum mechanical formalism, are related by a Fourier transform. Fourier's mathematics provided the precise language for one of the deepest and most counterintuitive truths about the fabric of reality. While the analytical method Fourier pioneered embarked on this spectacular journey of generalization, the original differential equation he sought to solve retained its own profound and enduring importance. The heat equation, expressed as the partial derivative of temperature with respect to time being proportional to the sum of its second partial derivatives with respect to spatial coordinates, its Laplacian became a paradigm for a whole class of physical processes known as dissipative systems. These are systems where energy or some other quantity spreads out, smooths over, and tends toward equilibrium. The same mathematical structure describes the diffusion of a drop of ink in a glass of water, the spread of a pollutant in the atmosphere, and the propagation of a gene through a population. In a striking example of interdisciplinary migration, a variation of the heat equation became the cornerstone of modern finance. The Black-Scholes equation, which won its developers a Nobel Memorial Prize in Economic Sciences, models the price of financial derivatives over time. It describes how the value of an option diffuses through the space of possible stock prices, its mathematical form bearing an unmistakable family resemblance to the equation Fourier wrote down to describe heat flowing through a metal plate. From the temperature of iron to the price of a stock option, the same elegant differential logic applies, a testament to the unifying power of mathematical description. Fourier's investigation, born from a specific query about the transfer of caloric fluid, had yielded a universal tool for understanding composition and a master equation for describing diffusion, demonstrating with unparalleled clarity how the pursuit of a particular physical truth can illuminate the universal structures of the mathematical world. The intellectual journey of Joseph Fourier culminates in a place of profound synthesis. His work, originating from the tangible problem of heat propagation, ultimately provides a universal grammar for understanding the world, a grammar whose vocabulary consists of waves and whose syntax is governed by the laws of diffusion. The analytical tools he forged possess a reach that extends far beyond their initial application, demonstrating how a focused inquiry into a particular physical phenomenon can yield a framework applicable to the cosmos of human knowledge. His legacy is one of transformation, offering a new way to perceive, to analyze, and to reconstruct the complexities of the physical and abstract worlds. Fourier's central achievement lies in a powerful conceptual duality. He furnished science with a method for deconstructing intricacy into its constituent simplicities, and simultaneously he provided the definitive mathematical description for a fundamental process of nature. The Fourier series and its continuous counterpart, the Fourier transform, embody the principle of decomposition. They reveal that any function, however irregular or seemingly chaotic, can be expressed as a sum, an infinite superposition of elementary periodic waves, sines and cosines. This is an idea of staggering philosophical weight. It suggests a hidden order, a harmonic structure underlying the apparent randomness of the universe. It is a form of analytical atomism, where the elementary particles are frequencies. Before Fourier, a musical chord was understood as a sum of pure tones. After Fourier, the very shape of a plucked string, the temperature profile of a cooling bar, the fluctuations of a market, and the light from a distant star could all be perceived as chords, each a unique symphony of pure, eternal frequencies. Complementing this tool for analysis was his formulation of the heat equation. The partial differential equation, dl squared U equals 1 over alpha times the partial derivative of U with respect to t, is an archetype of physical law. It is a statement about process. It describes how differences, in this case of temperature, smooth out over time, how systems evolve towards equilibrium. Its elegance lies in its local character. The change at any point depends only on the state of its immediate neighborhood. Yet from this local rule, a global evolution of extraordinary complexity emerges. This equation became the paradigm for all diffusion processes, describing the spread of a chemical in a solution, the movement of a population, or, as we have seen, the probabilistic drift of a financial asset's value. The heat equation is the poetry of equilibration, a mathematical expression for the universe's tendency to iron out its own wrinkles. The enduring vitality of these contributions is evident across the entire landscape of modern science and technology. Fourier's mathematics is the bedrock of signal processing. Every time we listen to digitally compressed audio, view a JPEG image, or speak over a mobile phone, we are beneficiaries of his insight. The raw data of sound and light are torrents of information. Fourier analysis allows engineers to transform this data into the frequency domain. In this new representation, essential information can be separated from noise, and the entire signal can be compressed by discarding the frequencies that are imperceptible to human senses. The digital world, in a very real sense, speaks in the language of Fourier. This same principle empowers some of our most advanced medical technologies. Magnetic resonance imaging, or MRI, builds its images from the world of frequencies. The human body is placed in a strong magnetic field, and radio waves are used to excite hydrogen nuclei. As these nuclei relax, they emit faint radio signals whose frequencies depend on their precise chemical environment and location. The MRI scanner collects these signals, a complex waveform containing a jumble of different frequencies. The machine then performs a sophisticated high-speed Fourier transform, converting this time domain signal into a frequency domain map. This map is then translated back into a spatial image, revealing the intricate structures of living tissue with breathtaking clarity. The physician looking at an MRI scan is, in effect, looking at a picture painted by Fourier's mathematics. Furthermore, the heat equation itself continues to find new and urgent applications. Its original domain, thermodynamics, remains central. Materials scientists use it to model the thermal properties of new alloys and composites, predicting how they will behave under extreme conditions in jet engines or spacecraft. The principles of heat transfer are fundamental to designing efficient cooling systems for everything from microprocessors to power plants. In a broader context, sophisticated versions of Fourier's equation are indispensable in climate science. Modeling the flow of thermal energy through the atmosphere, the oceans, and the polar ice caps is a problem of heat diffusion on a planetary scale. Understanding global warming requires mastering the complex dynamics of energy balance, a direct intellectual descendant of Fourier's investigation into a heated metal ring. The legacy of Jean-Baptiste Joseph Fourier, therefore, is one of profound connection. He was a figure who bridged the perceived chasm between the world of pure mathematical forms and the world of concrete physical problems. His work is a powerful argument that these two worlds are deeply intertwined, each enriching and giving meaning to the other. He began with a practical question, born of the industrial age, and in answering it, uncovered mathematical structures of timeless beauty and utility. His approach resolved the fierce 18th-century debate over the nature of functions, expanding the mathematical universe to include the discontinuous and the arbitrary, and in doing so, he laid the groundwork for much of modern analysis. He gave us a lens through which complexity resolves into simplicity, a tool that allows us to find the hidden pulse in the noise. His work embodies the spirit of the Enlightenment, the belief that the universe is fundamentally intelligible, that its most daunting phenomena will yield to rational inquiry and the power of mathematical description. Looking back from the vantage point of the 21st century, we see his influence woven into the very fabric of our technological civilization. From the equations that predict the climate to the algorithms that connect our world, the ghost of a French mathematician, once preoccupied with the flow of heat through iron, remains an architect of our modern understanding. His work stands as a permanent testament to the power of a single elegant idea to illuminate the world, revealing the simple harmonic beat that underlies the rhythm of existence.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.